Assalamu alaikum, my dear students. I am back again with part 2 of chapter 4. We ended up our last part with the conceptual example 4.1 in page 77, and I left it to you. I hope you guys understood that example, and we can see as I go through the book pages. And again, we are going through introduction of the chapter, screening of the chapter, and still we didn't do diagrams. We haven't done any kind of vector explanation or any kind of numerical examples. I know that, but this is just the introduction of the chapter. And in this section 4.3, if you see here, it is a caution. It's to distinguish between mass and weight. I think there's a very big misconception always that when you step on the scale and you say, oh, my weight is, okay, you are not doing here any mistake. When you say my weight is, for example, 60 kg, you're doing the mistake. I hope you can figure out. Again, I say, you step on the scale and you say, my weight is 60 kgs. Can you figure out where's the problem here? You are reading something which is correct. It is the weight, which is the force of gravity. Force of gravity, which is mg. So actually, you are not really supposed to say at the end kilograms. You are supposed to say, my weight is 60 Newton. 60 Newton. But this is a kind of common mistake that everybody is familiar with it, that even though it's a mistake, but we use it. So this is what is familiar for the street man. But we have to know that it's a mistake. Well, what will happen if you go to the moon? First of all, if you will be able to step on a scale, because you could not even step on the scale because of the very low gravity, your weight will be much less than that 60 kilo, whatever you call it, 60 kilograms. It will be much less. Maybe if you are weighing 60 Newton on the earth, it could be around 10 Newton on the moon, because the gravity of the moon is almost 1/9 of the gravity of the earth. All right, so your weight will be different from place to another, but what is constant? What is the thing that will not change? It's your mass. So either if you are on the earth or on the moon or on Mars, your mass will be the same, but your weight will be different. So the mass is a property of the body. It won't change, but your weight will change because, again, weight is mg on the earth, or m times a, which is the acceleration on the moon, or ma, the acceleration on Mars, if there is any. So I hope that I make it clear. And there are very good slides on the PowerPoint. You can refer to that, and they keep going on and on about the difference between weight and mass. Now we will go to Newton's second law of motion, which we mentioned in the beginning of the class, that it is F is equal ma. And if I will be more precise, I will say F net is equal ma. Again, F net is the net forces acting on the body. Which body? It's the body with mass m. M is the mass, A is the acceleration. So here is Newton's second law. This in light beige or something, this color. F, and you can see the mathematical notation, which is sigma. What is the meaning of sigma? The symbol sigma is the Greek letter sigma, and it stands for sum. So it is the sum of F. And that will emphasize more on the word net force. So this is the net force, or in other words, we say the sum of, it means all the forces acting on the object. Which object? It is the object with mass m. So in Newton's second law of motion, you can read this paragraph here. It's very clear. You can read it and you can see Newton's second law of motion from different kind of rephrasing. But here, this is the very known Newton's second law, which is the net force. This is the net force, which is the summation of all forces along that are acting on the object M. And by the way, we could have more forces, but we don't care. We do care at the moment that what are the forces that acting on the object of mass M. Okay. And that force will cause that object to accelerate. Or it would, let's see here the equation again. If there is a net force here, if this is a number, then this is the net force which will cause the object M to move with an acceleration of A. What if this net force, like we have a couple of forces acting on the object M, but as total, the net force is 0. It means object M will not move. Because if F is 0, it means A is 0. Can you tell that from the equation? If this part is 0, sorry, not this part, this whole part is 0. It means one of these two should be 0. Mass could never be 0 or negative, and that is very known. And the acceleration, it could be 0. So if the net force is 0, it is only one choice that we have. It means that the object is not moving. The acceleration is 0. Great. Now, if the object is moving along one dimension, it means we have a normal, like, a surface, and the object is moving left or right, or of that matter even if the object is moving up or down. So we are considering this motion as one-dimensional motion. We can just simply leave out, first of all, we can leave out, okay, let me say that again. Actually, we have forces along the x-axis, we could have forces along the y-axis, and also along the z-axis, but we are not concerned about the third dimension now. In Physics 1, we are only concerned about 2 dimensions. So we could be having forces up and down. We could have, which is here, the summation f sub y. We could have forces left and right. All right. If we are moving in one dimension, let's say that an object is moving along the x-axis or on the surface of a table. We don't need really to mention that it is sub x here, sub x. We can just simply say it is the summation of f, which is the f net is equal ma, because we are simply in one dimension. But once the object is moving in 2 dimensions, let's say, as an example, an object is running down, or it is moving down an inclined plane. What is the meaning of inclined plane? That's a plane with an angle. So that means that there are 2 dimensions for the motion, and there could be forces along the x and along the y. Then we have to literally say we want to see the forces along the x-axis and the forces along the y-axis. And pay attention to one thing. If these are the forces along the x-axis, then this is the acceleration along the x-axis. All right? If we are considering the forces along the y-axis, so we are mentioning the subscript y, it means also we have to consider the acceleration of the movement of the object along the y-axis. Okay, we will come in details once we come to some examples. I will leave these kind of tables which are very well explained to you to go through it. One very important thing here is the unit of our main concept in this chapter, which is force. We all know that it's a Newton who basically talk about force, who invented the laws of motion. So the unit of force is Newton. If you see here, what is F net again? It's M times A. What is the unit of M? It is kg. What is the unit of A? Meter per second square. So if somebody will ask us, what is a Newton in SI units? You know, Newton is not an SI unit. In Newton, you can say that in Newton, if you remember the first chapter or second chapter, I don't recall now, in the SI units, it's mass, time, and distance. So we have meter, kilogram, and second. So how to express Newton in SI units? It is kilogram, which is from the mass, times meter per second square, which is coming from the acceleration. This is very important to know, by the way. All right. And here you can see that there is an example. You can go through this example, but you have to pay attention that if we have a mass in grams and you are asked to find the acceleration, then you have to convert it into kilogram, because again, Newton is in kilogram meter per second square. All right. Now, we come to example 2. I will not go through the simple examples because that is your chance to go through them. But I can just go simply to read the example itself. Estimate the net force needed to accelerate a 1000 kilogram car at half g. It means m is known, which is 1000 kilogram. Acceleration is known, which is half g. What is half g? It is half times 9.8 meter per second square. So you just multiply them, and there we go. We find the net force on that object. Now, B, 200 grams. So first of all, you have to convert this into kilograms. And it says a 200 gram apple at the same rate. It means the acceleration is also for that apple is half of the gravitational acceleration, which is half times 9.8 meter per second square. And you will see the huge difference that for that object, which is 1000 kilogram, you need a force of 5000 Newton to accelerate it to half g, which is 5 basically, because half, approximately half times 9.8 is 5. While for moving an apple, which is almost 200 grams, with the same acceleration, we only need 1 Newton to move that apple with that acceleration. So you can see that if we are dealing with the same acceleration, then of course the force will be proportional with the mass of the object. Now this example will really give you a good example for merging between chapter 2 or 3. Now I don't recall. You know, the equations of motion. I think all of you recall these kind of equations with a Newton's second law. I will leave it to you. It's a very nice merge between these two chapters. I have to end my recording now because it it goes is 15 minutes, and I will see you again in part 3.